Okay, for section 8.3, we are answering the question, how are improper integrals evaluated? And so part of this lesson, I think, will be sort of counterintuitive. We'll think, like, how could this even have an answer? But the way that we figure out, I think, will be somewhat intuitive, and you'll see how that's carried out. So the first question is, what would be defined as an improper integral? There's two families of improper integrals. One would be infinite integration limits. Now, what I decided to do was just refer you to a nice little summary box on that, so that's on page 434. But when we're talking about infinite integration limits, we're talking about an integral that either has an upper limit of infinity, a lower limit of infinity or negative infinity, or one of them that way. So if you were integrating from 1 to infinity, something like that. So that would be that first family. The second family would be functions that have infinite discontinuities. So perhaps your limits of integration are okay. So let's say we're integrating from 0 to 7, but we're integrating something like 1 over x minus 2. Now, 1 over x minus 2, there's a discontinuity at x equals 2 because you'd be dividing by 0. And if you look, you'd have 1 over 0, so that would be an infinite discontinuity. Now, one would think that these integrals, or think of them as areas, right? They would never exist. How could it go out to infinity? Or if you have an infinite discontinuity, how could that possibly have a value? But that's not always the case. So that's where it might be counterintuitive. These do have values a lot of times, and that we would be surprising. We'll look at one right away that does. These is spelled T-H-E-S-E. Now, a couple little vocab words, and we're going to use these words a lot in the coming weeks, and that's the words converge and diverge. So if that integral exists, we say that it converges. If it does not exist, we say it diverges. So a question that might ask, does an integral converge or diverge, is really just asking, does it have a value or does it not have a value? Well, let's look at one. So find the area between the x-axis and y equals e to the negative x over 2 from 0 to infinity. Sounds like an impossible question. Let's take a quick look at the graph. Okay, so we're going to plot that. Real simple to do on y equals, let's clear some stuff out, and e to the negative x over 2. And we'll do a zoom 6 on this thing to start. And so it's an exponential decay graph. So what we're looking at, let's kind of zoom in a little bit. I'm going to do it kind of manually. So I'm going to change my x min to -1 and my y min to -1. So we can just see a little bit more of the graph. Okay. We see a lot of blank space up above, so maybe I can change my y max to something like 3 just to get rid of some of that blank space. Okay, so what we're looking at is this stuff in here where the pointer is. That area all the way out to infinity. Well, again, you might think that this thing goes on to infinity. I'm always adding area, so this must not exist. Well, let's just kind of carry it out here. So if we were setting up an integral, it'd be the integral from 0 to infinity of e to the negative x over 2. Now here is the procedure. It is a little different than you'd think, and again, you can kind of work through it intuitively, but what we do is we kind of write it from a limit perspective. We'd say the limit as x approaches b, whoops, that's supposed to be a b, in the integral from 0 to, wait, I'm messing that up. Erase my integral. It won't get, there we go. Okay. The limit, let me just change my limits of integration first. So instead of 0 to infinity, we'll write 0 to b of e to the negative x over 2 dx. But what we're looking at is that b value is approaching infinity. So that way we have sort of a placeholder instead of this, fuzzy infinity thing. So we look at our antiderivative. So the antiderivative of e to the negative x over 2, well, that would be itself. but we have to undo the chain rule. So we're going to try and work through without a u substitution. If I took the derivative of e to the negative x over 2, I would be multiplying by a negative 1/2. But there is no negative 1/2 in this, so that must have meant that there was a negative 2 out in front, the reciprocal. And so then we're going to evaluate that from 0 to b. So we've got negative 2e to the negative b over 2 minus negative 2e to the 0 over 2. Well, let's simplify that a little bit and clean it up a bit. We've got negative 2e to the negative b over 2. Now over here, 0 over 2 is 0. E to the 0 is 1. And negative 2 times 1 is negative 2, but it's minus a negative, so it is plus 2. But don't forget, we're taking the limit as b approaches infinity. So we're really looking at this thing and just picturing an infinity plugged in. Now, if you look at that exponent, b, if that was an infinity, it'd be e to the negative infinity. A negative exponent reciprocates, so e to the negative infinity, basically 0. So this whole first term right here goes to 0. Final answer, 2. So it actually has a value, and that value is 2 for that total area. Again, you might think, how is that possible? One of the things that I would say, I would explain it would be looking at just a series, which I think you would have done in Algebra 2, and thinking about the perspective of if, let me just use a pizza, if I were to bring a pizza to class, and the first person ate half of the pizza, and then they handed it to the second person, and they ate half of what was left, which means they ate a quarter of the pizza, and then the next person ate half of what was left. That was 1/8 of the pizza, and then the next person ate half of what was left. Hopefully at your stage of the game it wouldn't take too much to remember or decide that that can go on forever, but you'll never finish the pizza. So eventually that basically gets as close as possible to 1. It never will reach 1, but it gets really close to 1 whole pizza. All right, real quick, we'll look at a couple other ones, and then we'll proceed from there. So first one, does the integral from 1 to x of dx over x converge or diverge? This one's a little more straightforward. Again, I'm going to be kind of formal and use that limit idea. So the limit as b approaches infinity. We usually use b if we're replacing an upper limit, a if we're replacing a lower limit, of 1 to b of 1 over x dx. Okay, so antiderivative would be natural log of x evaluated from 1 to b. Don't forget we're taking the limit as b approaches infinity. So we've got natural log of b minus natural log of 1. Well, the natural log of 1 is indeed 0, but the natural log of infinity is infinity. So if you have infinity minus 0, that is infinity. This one diverges, so there's one that doesn't have a value, and that's what will happen in many cases. One or two more. We'll see what we can squeeze in within our time frame here. So when you have two limits of integration like that, it's often common to split it anywhere. Now, what would be a common place to split it? How about 0? So we would look at the integral from negative infinity to 0. And then the integral from 0 to infinity. If that's the case, we can now proceed by picturing a limit for our upper and lower limits there that are infinities. But look at this antiderivative. It is just tan inverse x. Again, hopefully you remember all your antiderivatives, but that's tan inverse. So we've got an antiderivative of tan inverse of x evaluated from, well, now I'm going to be a little sneaky, bring in the limit part. Let's just go from a to 0, and we're taking the limit as a approaches negative infinity. We're adding to that the antiderivative over here also tan inverse x. We're evaluating it from 0 to b, but we're making that b approach infinity this time. So what do we got? We got tan inverse 0 minus tan inverse a plus we've got tan inverse b minus tan inverse 0. So the tan inverse of infinity, if you work through the tan inverse of infinity, actually let me take it from a different approach. Let's take care of this tan inverse of 0 first. If the tangent has a value of 0, that would mean the sine has a value of 0. So these are zeros. Here and here. For the tan inverse of negative infinity, because we're having a approach negative infinity, I'll let you maybe play around with your calculator or check that out, or think backwards with the unit circle, but that would actually be negative pi over 2. So we have minus negative pi over 2. Here, the tan inverse of b, remember is going towards infinity. If we're plugging a really, really large number in for tan inverse and then working backwards, that means basically the angle is pi over 2, or 90 degrees if we're thinking in degree mode. So we've got minus a negative pi over 2, that's plus pi over 2. Added to that, another pi over 2. This actually has an area of pi. That is crazy to me. If we were to look at that graph, 1 over 1 plus x squared doesn't look like anything too special, but it has an area underneath it between the x-axis and the curve from negative infinity to infinity, and that area actually works out to be pi. Pretty amazing. Well, we're using a lot of time, so we'll save this next example for perhaps in class or perhaps later. We might have a second video on this section, and there's one other big thing to look at, and that is if you got really messy problems to work with, maybe there's a better, if your idea is just does it exist or not, we can do some tests to do that. One of them is called the direct comparison test, one of them is called the limit comparison test, and we will look at that together too.